So our next step is to open the file. Here I am using Notepad++ and we'll go directly to arbiter finite state machine, and the extension is SV, that means system verilog file. So here it is. Here I am making a package my types, where to fulfill the requirement of one hot encoding I have made these 7 states: idle, master 1, idle 1, master 2, idle 2, master 3 and idle 3, and each one has 1 bit high out of these 7 bits, which is called one hot encoding of state machine. Now I am importing my types as a whole, so this I will also use during the assertions as well. Now here I have the module. It's clock, reset, frame, I ready, request 1, request 2, request 3, grant 1, grant 2, grant 3, and state out. This state is just for monitoring what is the state inside. Here you can see in system verilog this logic is used instead of wire and reg. In fact, it creates a lot of confusion. So like we have in VHDL standard logic and standard logic vector, here a new type has been introduced, which is called logic. So my inputs are of type logic, clock, reset, frame, and iReady. Input also request 1, request 2, request 3, and my output logic is done, grant 1, grant 1, grant 3. And then to have the state, so I will give it the type of my states. So I can use these names. Initially in Verilog 2001, we name basically by using parameters, but here it is more like in VADL where we have enumeration type, and this is what is new in system Verilog. So here we have created a state register. As we already know that a state machine is made up of input logic, state logic, state register, and output logic. So if we are 0 on reset, this means that reset is active on when it is low, so we are in idle state. Otherwise we have the next state will be assigned to this state variable. Coming to this the state logic, we see that normally we will be in idle, and then in case of if we see different states at idle, if request 1 is 0 means it is active low signal, so when request is there it means it will be 0. Then our next state will be master 1 here. However, if we see that request 1 is inactive, which is at logic 1, and request 2 is 0, then we'll move on to master 2 state here. And the other option is that okay, we don't have the request from first user and also from the second user, then we'll say we have request from third user. So if request 1 is 1 and we have 0 on request 3, then we'll go to master 3, otherwise we will keep on moving in this idle state. Will remain in state master 1 till the time the done, if not of done. So if done is not asserted, then our next state will be remain in master 1, else we'll go into the idle 1 state, means that we have served the first user. In idle 1 we'll say see if request 2 is 0. This is the round robin thing, that we are giving priority to request 2 now. Here we are in fact making the priority encoding. So if second user is requesting, then our next state will be master 2. Else if master 2 is not there, then we'll give preference to uh, third user. So if it is 0 and request 2 is 1, our next state will be master 3. And then if there is no request from third user and not from second user, then priority will be given to first user to fulfill his request, and will go to the master one. Else next will be idle, means it will remain in this state. So we are making all cases, since we are making our combinational logic. So once we are in master 2, if done is not there, the things done in fact is indicated that all the transactions have all been been served. So will go into master 2, will remain into master 2 state, else will go into the idle 2. Same as in case of idle 1, here we'll see if request 3 is there, because now after second we have to see that third user is giving a request or not. If third one is there, then we'll go into master 3 state. Otherwise we'll see if this request 3 is 1 and request 1 is 0, then we'll go to the master 1. And finally if there is no request from user 1, then we'll look for the user 2 and 1. So if we have a request from third user, then we'll go to master 3, and here we'll wait when this done goes high. So as long as this done is low, we keep ourselves within this state, otherwise we go to idle 3. And here again we see if request from the first user is there, so we'll go to master 1. If first user is not there, then we'll check for user 2. If it's not there, then we'll check for user 3, else we'll remain in this state. So this was all about our state machine. So here we have the register, here we have this next state logic, and finally here we have some outputs. This is the internal signal. This done is asserted when we have an input frame is frame and iReady. So in these cases done is asserted and used in the state machine. And this signal is basically to see the states, just for verification, to see in which states the signals are moving. And finally here is the output logic. So grant 1 will be 0. It is also logic low valid signal. So grant 1 will be valid when it is low, and it will be low when the system will be in master 1 state, and grant 2 will be when system is in state master 2, and grant 3 will be valid, means 0, when the system will be in the master 3 state. So hence in this small example we created an FSM, where an FSM is basically made up of next state logic, then state register, and then we have an output logic. So this part was the state register, this part was the next state logic, and finally this was the output logic of the system.